action. Right. Let's start with some binomials. We know from our work at C1, C2, at AS, that we've got a plus b to the power n, where n is an integer, a positive integer, and we have this expansion. And NC0, NC1, NC2, etc. refer to Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. Okay? And in order to do this expansion, if you want to find the first three terms when n is 30, we can expand that out. So some revision from AS. Now, if a is 1 and b is x, then we have this result here. So NC0 would always just be 1, and NC1 is going to be n, and NC2 will be n factorial divided by n minus 2 factorial divided by 2 factorial times, let's just get rid of this, times 1 to the power n minus 2 times x squared. And if we carry on, we'll have n factorial divided by n minus 3 factorial times 3 factorial times 1 to the power n minus 3 times x cubed. If you were to tie that up, that will give us 1 plus n times x plus n minus 1 divided by 2 factorial times x squared. Just give me a second. And you've got n minus 1, n minus 2 divided by 3 factorial times x cubed, and on. And we have a pattern. What was the question?
How do you get from n factorial over 2 factorial n minus 2 factorial?
Right, so from here to here, right, so as you can see, I've got n factorial at the top. So n factorial means n times n minus 1 times n minus 2 on and on, factorial divided by the n minus 2 factorial times the 2 factorial. So the n minus 2 factorials will cancel out, and I'm left with n minus 1 divided by 2.
Because anything left.
Yeah, will cancel out. And then so we have this pattern here. And what we're basically saying is that when you've got 1 plus x to the power of n, then it falls into this nice expansion over here, and you can see the pattern where x goes up in powers, and you've got n minus 1, n minus 2, etc. divided by corresponding expansions. Now, at AS, what we've said so far is n is a positive integer. Okay, n is a positive integer, and that's the story so far. That's where we left off from AS. Is that okay? Any questions? Okay. All right. At A2, we're going to pose a question. What if n is negative for a fraction? So what if it's negative or fraction? Will it still work? What's going to happen? And our answer to that is that it will work, but only under certain conditions. So let's just start by doing an example, and then we'll explore the conditions. Now, with the, if I just write this, if I just copy the formula over here, let me just put this in. So this is like the standard expansion formula. Okay, where we can expand something out. Okay. Now, is this an infinite series or a finite series? Does it go on forever? Arisa, how do you know?
You just go up. Oh, in that one.
Yeah. Is
if
it that
n was 5, we'll just go up to 5.
if n was 5?
For example.
Yeah. Oh, x to the power of x will go up to 5?
Yeah.
Okay. What other thing can you see that tells you it's finite or you think it's infinite, why makes you say it goes on forever? Callum, you was going to say something?
It's only going to do it to, I think because there's 2 terms inside the bracket, it will only do it to the power of n, like different elements wrapping together.
Okay. Yeah, I think, yeah, but then n was 5. Let's just make n equals 5. What's going to happen to this? So you've got 5 times 4 times 3. What's the next one going to be? 5 times 4 times 3 times 2. And the following one will be 5 times 4 times 3 times 2 times 1. And then 5 times 4 times 3 times 2 times 0. So at some point, you'll get 0. Okay? And therefore, you'll have a finite series. It's not going to go on forever. If n is a positive integer. It won't go on forever. Okay? Because it's a now, if n is a fraction, then it may well go on forever. Or if n is a negative number, as you'll see in a second, then it will go on forever. And that means, well, hang on, if you've got an expansion, I'm saying 1 plus x to the power n, then wouldn't the numbers just get bigger and bigger? Let's explore that. Let's just start by doing a question. We'll do this one together, and then look at the conditions under which the expansion is valid. So say we had something like this, 1 plus x to the power of minus 3. Would you like to do this, or should we do it together?
Together.
Okay. So we simply plug and play. So this equals 1 minus 3x times minus 3 times minus 4. I'm using the dot to represent a multiplication. Divided by 1 times 2 times x squared. Plus minus 3 times minus 4 times minus 5. Divided by 3 times 2 times 1 times x cubed, and on and on. If we then tidy this up, we get 1 minus 3x plus 6x squared minus 10x cubed, and on and on. And the question we're asking, I'll put this in red, is that under what conditions is this valid? I.e., does it, if I put in a value of x, say I put in x equals 10, will this get bigger and bigger? I'll write the question. Does this go on forever? And therefore, will the terms get bigger and bigger? So let's see what this looks like. 1 plus x to the power minus 3. And if I was to plot it, this is what it looks like. This is the expansion. This is the actual function, sorry. 1 plus x to the power minus 3. If I then was to show you the expansion, this is what the expansion looks like. Let me get rid of the original function. This is, sorry, just a second. Yeah. This is what the actual expansion looks like.
What do you mean?
This, what we've just done here. 1 minus 3x plus 6x squared plus minus 2.
How come that's different from the original function?
Because it is. Yeah. So if I then show you the original function, that's what it looks like. The expansion looks like that. Okay. Now, what we can say is within a certain boundary, the gradient of both of them is actually going to be the same. The functions are essentially the same. If we were to show, like here's the working out, so this is what we end up getting. But we can quite clearly see that within the limits of minus 1 and 1, it offers a good approximation. It works. outside those limits, it's completely off. And what we could do, watch this, is you can see this text here. So what we're saying is between -1 and 1, it's a good approximation. Okay, the expansion is an approximation of the original function. Now, if we were to take a value of x, let's put in x equals 2 inside here. Look at my error margin. The relative error is, what is it? How many million? It's about 53 million. Okay, about just under 54 million percent.
No, it's not the same.
Percent.
It tends away,
Sorry?
even within those boundaries.
Yeah, we're coming on to that, yeah? Let me just talk about what's happening when x equals 2. Okay? You've got a massive error margin. Massive. And that's just when x equals 2. Let's see what happens when you put in something like 1.5. Still quite big. Not a good approximation. Okay? Let's see what happens when you put in about a 1. Okay? That's still massive, even at 1. But if we put something less than 1, let's try 0.8. Okay? Still about over 2,000%, the relative error. Okay? Let's try and focus in and go to 0.1. At 0.1, there isn't anything. It's really accurate at 0.1. Let's try 0.3. And as you can see, the relative error obviously is quite small. It's less than 1%. Okay? At 0.5, okay, and then it begins. It goes up to 13%. The same happens obviously at the negative values. If I put in a negative value of x, let's put in minus 0.3, and then I'll still get a small error margin. Callum.
Can you just differentiate both of the curves and then make them equal to each other to find where they're the same, where they stop being the same? Like in between 0 and 1.
I think it will complicate. You could try it out, but I think I think it's way too complicated to start, especially with some of the functions we'll see that you'll be getting, where you've got a combination of binomials in some sort of algebraic fraction. But I guess in theory you can, but it's a lot easier just doing the expansion. A lot easier. Okay, once you understand the concept of the limit. Now, you don't need to go into this in too much depth. In some, like in an Edexcel textbook, it actually said the discussion of the limits is beyond the scope of the book. But I just want you to appreciate the concept of a limit and the fact that the expansion meets the actual expression within certain limits, and it's a good approximation within those limits. Okay, and outside that, there's obviously a relative error. So what we basically say is that this expansion is valid for the absolute value, the modulus is valid when it's less than 1. Okay, and what this is basically saying is x has to be between -1 and 1. Okay, for a decent approximation. Okay, let's look at a couple of more examples.
So how do you get that? It's the modulus. Like from the question.
From the question will always be 1 plus something. It could be 2x like we've got here. It could be something x. You always take that 2x, so I'll do the next one in advance for you. So it'll always be 1 plus something. And in that case, you'll always take that something, and the modulus of that will always be less than 1. And so what you're saying is 2x is between -1 and 1, and therefore x is going to be between -1/2 and 1/2. And if you have to plot the 1 plus 2x to the power half against the expansion, you'll find that between -1/2 and 1/2, it's a good approximation. Not 100%, not perfect, but they're good margins to start using if you want to look at the expansion. Now, in terms of the expansion, do you want to have a go at this, or shall we do it together? I'll give you a minute. Have a go at it, and then I'll write out the answer. Let's see if we can get to the answer, and then we'll go over it together if needed. So your answer that you should get is 1 plus x minus 1/2 x squared plus 1/2 x cubed. Okay, so that's the answer you should get. And then this is the range. This is 1 mark in the exam. It's like the Plusion integration. And the expansion, so these are your limits. Okay, and the expansion is valid for those particular limits. So have a go at doing that, and I'll put up another one, and then we'll go over the answers again if needed. I'll even put this up. It's this one here. Okay. And the answer to this should be, so you can come up a bit. 1 over 1 minus x, 1 plus x, plus x cubed, where x is between minus 1 and 1. Let's have a go at doing example 2 together, and just see where you've gone wrong. So I'll do this step by step. We've got, let me take the pen out. So we've got 1 plus 2x to the power of a half. And this will be, if you go back to the formula, yeah, so 1 plus nx times n minus 1 over 2 factorial x squared, etc. So we've got 1 plus nx, so that would be half. Now my x part is going to be 2x. Okay. Plus the next part of the formula again is n times n minus 1 divided by 2 factorial. So I've got n times n minus 1 divided by 2 factorial times 2x, that x part all squared, plus n minus 1 n minus 2 times the x part cubed divided by 3 factorial. And if you tidy that up, you will get, remember, these parts here, you'll get, that becomes 2x. This part here is 4x squared. Okay, and this part here is 8x cubed. And so the corresponding coefficients, you should get 1 over 16 and 1 over 8, and that will just be 1. And then if you tidy that up, that will give you 1 plus x minus a half x squared plus a half x cubed. We've already established the limits, and let me just put that in. So this is valid for when x is between minus a half and a half. We have example 3. I'll leave example 3 for you to play around with, but I'll also show you example 4, which is a really good one. I'll even put this up here. Let me put it down first, and then give you a suggestion on how to do it. So here's example 4. Now notice with example 4, we don't have a 1 at the front over here. Okay? And that's a bit of a problem when you want to use our formula for the expansion. So what we need to do with example 4 is, if you've got a plus b to the power of n, we can take out the a, and so we've got b over a to the power of n. Okay, and using that result, we can rewrite the 4 plus x, and our final answer, I'll write down the final answer so you can have a go at doing it. It should be 2 plus x over 4 minus x squared over 64 plus x cubed over 512. And the limit, well, I'd like you to tell me what you get. I'll leave it as a question mark for the moment. And you've got enough information there to also do example 5. Let me just put that in. And I'll leave this as an extension. It's this one here. Okay, let me just make that. So zoom out a bit. Okay, and the final answer for 5 is going to be 1 plus 3 over 2x plus 3 over 8x squared, and the limit, I want you to tell me what you get, and it's quite an interesting little discussion we can have. Okay, so I'll let you finish that off. And then we'll go over it if needed.